Tonight, we're going to place our entire galaxy next to the structure that actually contains it. The Milky Way is a spinning disk of stars, gas, and dust, home to everything we've ever seen with the naked eye, every constellation, every star system that's ever been named or mapped. From the inside, it feels like the whole of existence. It's the backdrop to every night sky anyone has ever looked up at, the source of every point of light we've learned to recognize. And yet, against the true scale of the universe, our galaxy is a much smaller piece of the picture than anything you can imagine. By the end of tonight, you're going to understand exactly how small our galaxy really is, how it fits inside groups, clusters, superclusters, and finally the observable universe itself, and why the true size of everything that exists might be a number we can never actually know. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Start with something familiar. Stand outside on a clear night, somewhere dark enough that you can actually see the sky, and look up. There's a faint band of light cutting across the darkness from horizon to horizon. That band is the Milky Way. Not the whole Milky Way, because you're inside it. What you're seeing is the combined glow of billions of stars, so distant they merge into a single wash of light. The disk of our galaxy, seen edge on from within. Now, the Milky Way is what astronomers classify as a barred spiral galaxy. It has a flat disk of stars, gas, and dust, wound into sweeping spiral arms that wrap outward from the center. At the heart of the galaxy is a dense central bulge where stars are packed together so tightly that a planet orbiting near the core would never experience full darkness. Even at night, the sky would glow. Running through that bulge is a long, elongated bar of stars, a structure that extends across the central region before the spiral arms peel away from its ends. That's the barred part. And at the absolute center of everything, the gravitational anchor of the entire galaxy, sits a supermassive black hole called Sagittarius A. Its mass is roughly 4 million times the mass of our Sun. 4 million solar masses, compressed into a region smaller than the orbit of Mercury. The disk of the Milky Way spans about 100,000 light-years in diameter. Some measurements push that number a bit higher, to around 120,000 light-years, depending on where you define the outer edge of the most distant spiral arms. The disk is also extraordinarily thin relative to its width, only about 1,000 light-years from top to bottom in its densest regions. So, you have a structure that's roughly 100 times wider than it is thick. A dinner plate, scaled up to galactic proportions. Our Sun sits about 26,000 light-years from the galactic center. That puts us slightly more than halfway out from the core to the visible edge. Not at the center, not at the edge. We're in the suburbs. The Sun orbits the galactic center at about 500,000 miles per hour. At that speed, one complete orbit takes approximately 225 million years. Astronomers call this a galactic year, or a cosmic year. In the entire history of complex multicellular life on Earth, our Sun has completed roughly 2 full orbits of the Milky Way. Over its entire 4.5 billion year lifetime, it's only gone around about 20 times. The Milky Way contains somewhere between 100 billion and 400 billion stars. The range is wide because counting stars inside our own galaxy is genuinely difficult. We can't step outside and photograph the whole thing. We're embedded in the disk, surrounded by gas and dust that blocks our view in many directions. Dense clouds of interstellar dust absorb visible light entirely, hiding entire regions of the galaxy from optical telescopes. Infrared observations, which can see through dust that blocks visible wavelengths, have gradually expanded our census of the galaxy. But even with infrared, the mapping is incomplete. The lower estimate of 100 billion stars is already almost beyond the range of numbers our minds were built for. If you counted one star per second, without sleeping, without pausing, it would take you over 3,000 years to reach 100 billion. And most of those stars would be red dwarfs, dim and small, but burning for trillions of years. Some of the red dwarfs in the Milky Way today formed when the universe was young. They were there before our sun existed. They'll still be burning when our sun is gone. The Milky Way is not just enormous in space, it's enormous in time. Its oldest stars are over 13 billion years old. Its formation began shortly after the Big Bang itself. The observable universe is not the same thing as the universe. The universe itself, as best as we can determine, has no physical edge. There is no wall, no boundary, no place you could travel to and declare that this is where the universe ends and something else begins. What we call the observable universe is a different concept. It's the portion of everything that exists from which light has had enough time since the beginning to reach us. The universe is 13.8 billion years old. Light travels at a fixed speed, about 186,000 miles per second. So the furthest light that could have possibly reached us by now left its source when the universe was extremely young. Anything further away than that, light from it is still traveling toward us. It hasn't arrived yet. The sphere, defined by that limit, the sphere centered on Earth, within which light has had time to travel to us, is what we call the observable universe. Everything inside that sphere is, in principle, something we could observe with the right instruments. Everything outside it is, for now, beyond our reach. Not because it doesn't exist, because its light hasn't had 13.8 billion years to get here yet. Now, you might expect the radius of that sphere to be 13.8 billion light years, the age of the universe in years, times the speed of light. But the actual radius of the observable universe is about 46 billion light years. Not 13.8 billion, 46 billion. The reason for this discrepancy is one of the more mind-bending facts in cosmology, and it comes down to what space has been doing the entire time that light has been traveling. Space has been expanding. When a distant galaxy emitted light 12 billion years ago, that galaxy wasn't 12 billion light years away. It was much closer. But as the light traveled toward us, the space between us and the galaxy was stretching. The galaxy was being carried further away by the expansion of space, even as its light was crossing the decreasing gap. So when that light finally arrives, the galaxy that sent it is now much further away than the distance light could have crossed in the time available. It's as if you're trying to catch someone running away from you, and the ground itself is stretching beneath your feet. The light catches up because it was emitted when the runner was close enough. But by the time it arrives, the runner has been carried much further by the expanding ground. When you account for all of this, the most distant light we can observe today was emitted by sources that are currently about 46 billion light years away from us. The observable universe has a radius of 46 billion light years, a diameter of about 93 billion light years. Now, set that next to the Milky Way, 100,000 light years, versus 93 billion light-years. To get from one number to the other, you multiply by about 930,000. The observable universe is 930,000 times wider than our galaxy. There is no everyday analogy that fully captures what that means. The gap is too large for comparisons that stay within the range of human experience. What matters is understanding that the Milky Way, for all its hundreds of billions of stars, is a microscopic participant in a structure that outscales it by nearly a factor of 1,000,000. The galaxy isn't a uniform disk of evenly distributed stars. It has layers, different populations of stars living in different regions, each telling a different story about how the galaxy formed and evolved. The most visible and densely populated region is the thin disk. This is the flattened midplane of the galaxy, where the spiral arms are found, where the gas clouds are densest, where new stars are forming right now. Young stars live in the thin disk. Hot blue stars, recently ignited from collapsing molecular clouds, burning bright for only a few million years before they end their lives in supernovae. Open clusters, loose associations of a few hundred to a few thousand stars that form together from the same cloud and are still drifting through space near each other. And the molecular clouds themselves, dense regions of cold gas and dust where the next generation of stars is already taking shape. The Orion Nebula, about 1,400 light-years from us, is one of the most spectacular examples visible from Earth. A vast cloud of gas and dust lit from within by newly formed hot stars, with planetary systems assembling in its darker, cooler regions. Stars like our Sun may have formed in something similar 4.5 billion years ago. Beyond the thin disk is the thick disk. Older stars, more metal-poor, orbiting the galactic center on paths more inclined to the plane of the galaxy. These stars belong to an earlier era of the Milky Way's history, when the galaxy was younger and its shape less settled. They carry chemical signatures in their spectra that reflect the composition of the universe at the time they formed, before stellar generations had enriched it with heavy elements. Above and below the disk is the galactic halo, a roughly spherical region surrounding the entire galaxy. The halo extends tens of thousands of light-years above and below the disk and contains far fewer stars than the disk itself, maybe 1% of the galaxy's total stellar mass. But the stars in the halo are among the most ancient in the entire galaxy. Population 2, stars, as they're classified, formed when the universe was young and the chemical environment was almost pure hydrogen and helium. These stars are red and dim and old. They've been burning quietly for over 10 billion years. They were there before the solar system existed, before Earth existed, before the Sun existed. Many of these halo stars are gathered into globular clusters, dense, spherical collections of hundreds of thousands of stars packed into regions just tens of light-years across. If you could stand on a planet inside a globular cluster, the sky would be dazzling. Stars within a few light-years in every direction. The Milky Way has about 150 known globular clusters. They orbit the galactic center on sweeping paths that carry them through the halo and sometimes through the disk. Some are thought to be the remnant cores of ancient dwarf galaxies that the Milky Way absorbed long ago. The gravity of our galaxy stripped away their outer stars, leaving only the densely packed cores. Globular clusters are among the most useful objects in astronomy. Their ages set a lower limit on the age of the universe itself. If a globular cluster is 12 billion years old, the universe must be at least that old. Early measurements of globular cluster ages in the 1990s produced a historical curiosity. They seemed to be older than the universe, as estimated at the time. That pointed to errors in the measurement of the Hubble constant, the rate of cosmic expansion. Resolving the discrepancy required improving the distance measurements to nearby galaxies, which in turn led to a better value for the expansion rate, which led to the current best estimate of the universe's age at 13.8 billion years. The age problem is now resolved. Globular clusters are old, but the universe is older. Beyond the halo of visible stars is the dark matter halo, a vast, invisible structure extending far beyond anything you can see. The dark matter halo of the Milky Way is thought to reach out to somewhere between 500,000 and 600,000 light-years from the galactic center, 6 times the diameter of the visible disk. The dark matter halo is roughly spherical, enveloping the galaxy in all directions. Dark matter particles pass through everything constantly. Through the disk, through the stars, through your body as you read this. But because dark matter interacts with normal matter only through gravity, not through electromagnetism, not through the strong or weak nuclear forces, it passes through without any detectable interaction. We know it's there because of what it does to the stars we can see. The outer stars of the Milky Way orbit at speeds that only make sense if there's far more mass present than the visible stars and gas can account for. The dark matter holds them in. It is, in a very real sense, the skeleton of the galaxy. The visible stars and gas are the skin. The dark matter is the framework underneath. So the Milky Way is not just the 100,000 light-years of the visible disk, including the dark matter halo. It extends to 600,000 light-years in all directions. Still small compared to the observable universe, but larger than it first appears. The Milky Way is not alone in space. It belongs to a local family of galaxies called the Local Group. The Local Group contains about 80 galaxies in total, most of them dwarf galaxies, small collections of a few billion stars that orbit around the larger members. The 3 largest members are the Milky Way, the Andromeda Galaxy, and a smaller spiral called the Triangulum Galaxy. Andromeda is approximately 2.5 million light-years away. It's the most distant object visible to the naked eye on a clear, dark night, a faint oval smudge of light in the constellation Andromeda. When you look at it without a telescope, the light entering your eye left Andromeda 2.5 million years ago. You're seeing it as it was when our ancestors were making the earliest stone tools. Andromeda is a large spiral galaxy, similar in overall structure to the Milky Way. By some measurements, it's slightly more massive. By others, roughly comparable. It has its own supermassive black hole at its center, and its own population of hundreds of billions of stars. It also has its own retinue of satellite galaxies, and its own dark matter halo. And it is heading toward us. The Milky Way and Andromeda are moving toward each other, pulled by mutual gravity, at about 250,000 miles per hour. At that rate, they will begin to interact in about 4.5 billion years. The merger will be slow and gradual, unfolding over hundreds of millions of years. It won't look like a dramatic collision. Stars are too spread out relative to their sizes for many of them to physically strike each other. The interaction is gravitational. Long tidal streams of stars will be torn from both galaxies as they pass through each other. Spiral arms will be disrupted. gas clouds in both galaxies will be compressed by the collision, triggering bursts of new star formation. Over the course of hundreds of millions of years, the galaxies will pass through each other, then be drawn back together by gravity, then pass through again. Eventually, after a series of passes and interactions, they'll settle into a merged structure, not a spiral galaxy any longer. The rotation and structure that define spirals will have been scrambled by the interaction. The result will be a large elliptical galaxy, rounder, smoother, full of older stars with no ongoing star formation. Astronomers call this future object Milkomeda, or sometimes Milkdromeda. Our Sun will survive the merger. It will simply end up in a different orbit around the merged galaxy's center. The night sky from any planets orbiting the Sun in that era will look completely different from what it does now, but it will still have a sky full of stars. The Magellanic Clouds are among the most prominent members of the local group after Andromeda and Triangulum. The Large Magellanic Cloud sits about 160,000 light-years away. The Small Magellanic Cloud is about 200,000 light-years away. Both are visible from the southern hemisphere as fuzzy patches of light that look like detached pieces of the Milky Way. They are satellite galaxies, gravitationally bound to us and orbiting our galaxy over timescales of billions of years. The Milky Way's gravity is actively disrupting both of them. There's a structure called the Magellanic Stream, a long trail of gas being pulled out of the Magellanic Clouds by our galaxy's tidal forces, arcing across about 140 degrees of the southern sky. Over billions of years, both the large and small Magellanic Clouds will likely be absorbed into the Milky Way. Their stars and gas added to our galaxy's own reserves. The Milky Way has almost certainly done this many times before. There are stellar streams in the halo, long arcs of stars with similar ages and compositions that are the remnants of dwarf galaxies absorbed long ago. The Sagittarius dwarf, spheroidal galaxy, is in the process of being absorbed right now. It has already passed through the Milky Way disk multiple times, and stars torn from it trail behind it in a stream that wraps around the entire galaxy. Our galaxy grows by consuming smaller ones. It's been doing it since the beginning. The entire local group, with all its 80 galaxies, spanning about 10 million light-years, is the home neighborhood. 10 million light-years. 100 times the diameter of the visible Milky Way disk. And the local group is itself just one small component of a much larger structure. The local group is embedded in a larger structure called the Virgo supercluster. The Virgo supercluster spans about 110 million light-years. At its center sits the Virgo cluster itself, a dense concentration of over 1,000 galaxies, about 50 million light-years from us. The Virgo cluster is dominated by several enormous elliptical galaxies. The largest, Messier 87, contains several trillion stars. Several trillion. Its total mass is about 50 times the mass of the Milky Way. At its center sits a supermassive black hole with a mass of approximately 6.5 billion times the mass of our Sun. To put that in context, the black hole at the center of our own galaxy has a mass of 4 million solar masses. The black hole at the center of Messier 87 has a mass of 6.5 billion solar masses. It is over 1,000 times more massive. Its event horizon is so large that the entire planetary solar system, out past the orbit of Neptune, would fit inside it. In 2019, the Event Horizon Telescope collaboration released the first ever direct image of a black hole. The black hole they imaged was the one at the center of Messier 87. The Event Horizon Telescope is not a single telescope. It's a global network of radio telescopes spread across multiple continents and in multiple countries. From Hawaii to Chile to Greenland to Spain to Antarctica. By combining observations from all these instruments simultaneously, using the rotation of the Earth to build up a picture over time, the collaboration created a virtual telescope with an effective diameter equal to the diameter of Earth. That's the angular resolution needed to image a black hole 50 million light-years away. The resulting image showed a dark, circular region, the black hole's shadow, surrounded by a bright ring of glowing, superheated gas. That ring is material orbiting the black hole at nearly the speed of light. The temperature of that material is billions of degrees. Nothing in that ring survives long. It spirals inward and is consumed. Messier 87 also has a jet, a beam of matter and energy shot out from near the black hole at nearly the speed of light. That jet extends for about 5,000 light-years into the surrounding intergalactic space. It's made of electrons and positrons and magnetic fields, all accelerated to relativistic speeds by the black hole's enormous gravitational and electromagnetic fields. When those particles slam into the surrounding gas, they produce enormous lobes of radio emission visible across hundreds of thousands of light-years. The Virgo cluster contains over 1,000 galaxies like Messier 87, each with its own internal structure, its own black holes, its own stellar populations. The environment is violent. The space between galaxies in the Virgo cluster is filled with hot gas at temperatures of tens of millions of degrees. It's invisible to optical telescopes, but it glows brightly in X-rays. When a galaxy falls into the cluster at high speed, this hot intergalactic gas pushes against the infalling galaxy's own gas. The effect is called ram pressure stripping. It's powerful enough to pull the star-forming gas right out of a galaxy as it moves through the cluster. Stripped of its gas supply, the galaxy can no longer form new stars. Its existing stars age and fade. Over billions of years, the galaxy becomes red and dead, full of old stars, incapable of renewal. Many galaxies in the Virgo cluster, and in clusters like it around the universe, show exactly this signature. Red, quiescent. Their star formation ended the moment they fell too deep into the cluster's gravitational well. The Milky Way is not in such an environment. We're in the quiet outskirts of the local group. But gravity doesn't stop at the boundary of the local group. We're being pulled toward the Virgo cluster by its gravity. The entire local group is falling toward Virgo at about 140 miles per second. We're not going to get there. The acceleration of the universe's expansion will eventually carry the Virgo cluster beyond our cosmic horizon, faster than we can fall toward it. But the pull is real, and it's been shaping our trajectory through space for billions of years. In 2014, a team of astronomers announced a discovery that fundamentally changed how we understand where the Milky Way sits in the large-scale cosmos. The team was led by Brent Tully at the University of Hawaii. They had been painstakingly mapping the velocities of thousands of galaxies across a vast volume of space. Not just the velocities caused by the expansion of the universe, which carries every galaxy away from every other. They were mapping the additional peculiar velocities, the extra motions caused by the gravitational pull of nearby mass concentrations. Every galaxy in the universe has two components to its motion. There's the component from cosmic expansion, which pushes everything apart. And there's the component from local gravity, which adds motion toward the nearest concentrations of mass. By carefully subtracting out the expansion component, you're left with the peculiar velocities. And peculiar velocities tell you where mass is. They tell you which way things are being gravitationally pulled. Tully's team measured the peculiar velocities of over 8,000 galaxies. They found something remarkable. A huge volume of space, extending about 500 million light-years in all directions, was filled with galaxies, all sharing a common flow. They weren't just moving apart due to expansion. They were all flowing in the same direction, toward the same gravitational basin. Every galaxy in this enormous region was being pulled toward the same sink. That shared gravitational basin defined a coherent structure. Not a visible structure in the photographic sense. You couldn't just look at the sky and see its edges, but a structure defined by motion, by the gravitational influence it exerts on everything in its vicinity. Tully's team called it Lania Kea. The name comes from the Hawaiian language. Lani means heaven. Akea means spacious or immeasurable. Immeasurable heaven. Lania Kea contains about 100,000 galaxies. It spans about 500 million light-years. Our galaxy sits near its outer rim. Lania Kea is 5,000 times the diameter of the Milky Way. The gravitational center toward which all those galaxies are flowing is a region called the Great Attractor. It sits about 250 million light-years from us. For decades, astronomers knew something massive was pulling on our galaxy and everything nearby. The motion was measurable, but the source was hidden. The Great Attractor lies in a direction on the sky that happens to coincide with the plane of the Milky Way's disk. All the dust and gas in our own galaxy's midplane blocks our view in that direction. The region even has a name in astronomical cartography: the zone of avoidance. Not because astronomers don't want to look there, but because our own galaxy is in the way. Only in recent decades, with the use of infrared and radio wavelengths that can penetrate the dust, has the picture become clear. The Great Attractor is not a single object. It's a complex of galaxy clusters, with the Norma cluster at its heart. The combined mass of the whole system is equivalent to tens of thousands of Milky Way galaxies. But even the Great Attractor isn't the ultimate source of the flow. Beyond it sits the Shapley concentration, a supercluster of galaxy clusters about 650 million light-years from us. It contains over 8,000 galaxies and has a mass of roughly 10 million billion times the mass of the Sun. The Shapley concentration is one of the most massive structures in the observable universe within the range we can map precisely. And Lania Kea itself is being pulled toward it. Everything flows. The Milky Way is being pulled toward the local group's center. The local group is falling toward Virgo. Lania Kea as a whole is being drawn toward the Shapley concentration. Structure upon structure, each pulling on the next. We're not stationary in the cosmos. We're participants in a vast gravitational choreography. Zoom out further still, and the individual structures, the clusters, the superclusters, dissolve into pattern. At the largest scales, the universe has an architecture. It's called the cosmic web, and it's one of the most striking things that cosmology has revealed. The cosmic web is the name for the overall large-scale structure of matter in the observable universe. At scales of hundreds of millions to billions of light years, matter is not uniformly distributed. Galaxies are not scattered randomly through space, like stars in a galaxy. They're gathered into long, thin filaments, stretching across hundreds of millions of light years. These filaments intersect at dense nodes called galaxy clusters. Between the filaments are vast, nearly empty regions called voids. When you look at computer simulations of the cosmic web, or at actual three-dimensional maps constructed from galaxy surveys, the appearance is striking. The structure looks biological. It resembles neural tissue, or the inside of a sponge, or the arrangement of foam bubbles. Thin threads of matter connecting at points of concentration with dark, empty cavities stretching between them. It's a structure so elegant that it almost looks designed. It isn't. No designer arranged the cosmic web. The structure emerged naturally, from initial conditions set in the first tiny fraction of a second after the Big Bang, amplified over billions of years by gravity alone. In the very earliest moments of the universe, matter was distributed almost perfectly uniformly. But almost is the key word. There were tiny fluctuations in density, regions that were fractionally denser than their surroundings. These fluctuations had quantum mechanical origins. In the era of inflation, a period of extremely rapid expansion that occurred in the first fraction of a second after the Big Bang, quantum fluctuations in the energy field driving the inflation were stretched from subatomic scales to cosmic scales. They became the seeds of structure. After inflation ended, those seeds began to grow. Over hundreds of millions of years, and then over billions, gravity drew matter toward the denser regions. Dense regions attracted more matter, becoming denser still. Less dense regions shed their matter as gravity pulled it away, becoming emptier still. The denser regions connected into filaments. The emptier regions expanded into voids. The nodes where filaments intersected became the massive galaxy clusters. Over the full age of the universe, from the Big Bang to today, this process produced the cosmic web we observe. The first systematic evidence for the web came from galaxy surveys in the 1980s. At the time, astronomers had expected galaxies to be distributed roughly randomly through space. Maybe a little clustering here and there, but nothing organized on truly large scales. What they found was the opposite. Galaxies were arranged in sheets and walls surrounding enormous empty bubbles. The CFA Great Wall, discovered in 1989, was a filament of galaxies about 500 million light-years long. Later, the Sloan Great Wall was mapped in 2003, stretching about 1.37 billion light-years across. And then, in 2013, astronomers announced the discovery of the Hercules Corona Borealis Great Wall. Its estimated size is staggering, somewhere between 6 and 10 billion light-years in extent. If the larger estimates are accurate, it represents a single coherent structure spanning roughly 1/10 of the diameter of the entire observable universe. One structure, 10 billion light-years. To put it in terms of the Milky Way, the Hercules Corona Borealis Great Wall is approximately 100,000 times the diameter of our galaxy. Not the observable universe. Not the full cosmic web. One filament within it. 100,000 Milky Ways laid end to end. The cosmic web gives us the large-scale map of where the universe put its matter. The answer is mostly into thin structures surrounding enormous cavities. The voids are not small features. The Botez void is about 330 million light-years across. It contains almost no galaxies. A few scattered dwarf galaxies, isolated in a near-empty bubble, When it was discovered in 1981, it caused genuine surprise. The void was so large that it was hard to reconcile with existing models of how structure forms. At the time, the size seemed almost impossible to explain. Better models, driven by better data on dark matter and the evolution of the cosmic web, have since explained it. The voids are where matter used to be, before gravity drew it into the filaments. They're the complement of the filaments. Where filaments are the overdense regions that attracted matter, voids are the underdense regions that lost it. And they are, by volume, the dominant feature of the universe. If you placed yourself at a random point in the observable universe, not choosing where you land, just a truly random position, the odds are that you'd find yourself in a void. Most of the volume of the observable universe is void. Galaxies are clustered into the thin web of filaments that occupies a small fraction of the total volume. Everything else is a vast, dark, near emptiness. Our galaxy happens to sit not in a void, but in a region of modest density. The local sheet, as it's called, is a relatively flat arrangement of galaxies, including the Milky Way and its nearby neighbors. Not in a dense cluster like Virgo. Not in a void. In between, which turns out to be a reasonably comfortable place to be, at least for the formation and stability of a planetary system over billions of years. Dense cluster environments can disrupt planetary systems through gravitational interactions and high-energy radiation. Voids are too sparse in gas and heavy elements for complex chemistry to develop quickly. The suburbs of a filament, near a modest group of galaxies, may be a particularly suitable environment for the development of complex systems like planetary biospheres. Whether this has anything to do with why life exists here, or whether it's coincidence, is an open question. The number of galaxies in the observable universe is one of those figures that was dramatically revised upward in the recent past. And the revision itself tells us something important about how we study the cosmos. Before 2016, the standard estimate was somewhere around 200 billion galaxies. A large number, but it had been arrived at by measuring the density of galaxies in observed patches of sky and extrapolating to the full volume of the observable universe. The problem was that older instruments had detection limits. Small, faint, distant galaxies, the kind that form early in the universe's history, were too dim to detect in earlier surveys. The count was based only on what had been seen, not on what was actually there. In 2016, a team led by Christopher Consolis at the University of Nottingham reanalyzed data from the Hubble Space Telescope and other instruments. They used mathematical models to account for the galaxies that were present but below the detection threshold of current technology. The result was a revised estimate of about 2 trillion galaxies in the observable universe, 10 times more than the previous figure. 2 trillion. 2 followed by 12 zeros. Each one a galaxy, a vast system of stars held together by gravity, embedded in a dark matter halo, occupying some region of the cosmic web. Some are giants, larger than the Milky Way. Some are dwarfs, containing only a few billion stars. Some are blue and actively forming stars. Some are red and quiescent. Some are spirals. Some are ellipticals. Some are irregular, shapeless collections that don't fit any neat category. All of them are out there, spread across 93 billion light-years of observable space. If you counted one galaxy per second, it would take you over 63,000 years to count them all. And that's just the observable universe. The actual universe almost certainly contains more. How many more? We don't know. The count could be larger by any factor you care to name. The Hubble Space Telescope gave us one of the most vivid demonstrations of how full the universe actually is. In December of 1995, astronomers made a decision that seemed eccentric at the time. They pointed the Hubble Space Telescope at a patch of sky near the Big Dipper. Not at any known galaxy, not at any interesting nebula or cluster, at a completely blank, dark patch of sky. They left it there for 10 consecutive days, letting light accumulate from the faintest possible sources. What emerged from that long exposure was the Hubble Deep Field. In a patch of sky so small that you could cover it entirely with a grain of sand held at arm's length, there were approximately 3,000 galaxies. Not stars, not gas clouds, galaxies, some close, their structure visible as clear spirals and ellipticals, some at intermediate distances, smaller and less distinct, some so far away they appeared only as faint red smears, ancient light that had been traveling for over 10 billion years. The image was immediately understood to be transformative. It implied that every direction in the sky, no matter how blank it appeared to normal instruments, was full of galaxies when you looked long enough. Hubble later produced the ultra-deep field, a longer exposure of a darker patch, revealing over 10,000 galaxies. Then, the extreme deep field, which pushed the total to over 5,500 galaxies in an even smaller area. If you took the density of galaxies in the extreme deep field and extrapolated it across the entire sky, the implied total number of galaxies in the observable universe matches the 2 trillion estimate. The universe does not have empty patches of sky. It has patches of sky that appear empty to instruments that haven't yet waited long enough. The James Webb Space Telescope has pushed this further. Since delivering its first science images in 2022, Webb has been observing galaxies at distances that exceed what Hubble could reach. Its infrared sensitivity allows it to detect light that has been stretched by the expansion of the universe from its original, visible, or ultraviolet wavelengths into the infrared. This stretched light, called redshifted light, carries information about galaxies formed when the universe was less than 1 billion years old. Some of Webb's early targets have turned out to be more massive, more structured, and more chemically enriched than models had predicted for their age. The universe seems to have built large, complex galaxies earlier than our models expected. The details are still being worked out. New data arrives from Webb regularly, and each release adds to the picture. What's clear is that the early universe was not a quiet, featureless place. It was a period of intense activity, rapid star formation, frequent galaxy mergers, and the rapid assembly of structure. The universe we live in now is in some ways quieter than it used to be. The peak of cosmic star formation, sometimes called cosmic noon, occurred about 10 billion years ago. Since then, the overall rate of star formation across all galaxies has been declining. The universe was making new stars more actively in the past than it is now. It's gradually running out of the cold gas needed to form new stars. Galaxies like the Milky Way still form stars, but at a slower rate than they once did. The era of vigorous star formation is winding down. The universe is, in a cosmic sense, aging. To understand the gap between our galaxy and the observable universe, you also need to understand the role of dark matter. Because dark matter is not a peripheral detail. It's the majority of the matter in the universe. And the story of how we came to know it exists is one of the more revealing episodes in the history of science. The first serious evidence for dark matter came in the 1930s from an astronomer named Fritz Zwicky. He was studying the Coma Cluster, a massive collection of hundreds of galaxies about 300 million light-years from us. Zwicky measured the velocities of galaxies in the cluster by analyzing the Doppler shift in their light. When something moves toward you, its light is blue shifted. When it moves away, its light is red shifted. The amount of shift tells you the speed. The galaxies in the Coma cluster were moving at high speeds. But when Zwicky calculated how much gravitational force was needed to keep the cluster from flying apart at those speeds, he found a problem. The visible galaxies didn't contain nearly enough mass. The gravity of everything you could see in the cluster was far too weak to hold it together at the observed velocities. By rights, the galaxies should have been escaping in all directions. The cluster should not exist. The fact that it clearly did exist and had been holding together for billions of years meant something was providing the extra gravity. Something massive. Something he couldn't see. He called it Dunkel Materie, dark matter. The reaction from the scientific community was skeptical. Alternative explanations were favored. Maybe the measurements were wrong. Maybe there was ordinary matter in the cluster that just hadn't been detected. Maybe the laws of gravity needed revision on large scales. Then, in the 1970s, Vera Rubin and her collaborator Kent Ford began systematically measuring the rotation of stars within individual spiral galaxies. The basic expectation, derived from Newtonian gravity, was clear. Stars far from a galaxy's center, where most of the visible mass is concentrated, should be orbiting more slowly than stars near the center. The same relationship holds in our solar system, where the outer planets move more slowly than the inner ones. Mercury orbits the Sun much faster than Neptune because it's much closer to the gravitational center. But that's not what Rubin and Ford found. Stars in the outer regions of galaxies were orbiting just as fast as stars near the center. Sometimes faster. The rotation curves were flat, where they should have been declining. The only explanation that worked was that the galaxies were embedded in vast, spherical halos of invisible mass, mass that extended far beyond the visible disk of stars. Mass that provided the extra gravitational pull needed to keep the outer stars moving at those speeds. Dark matter. What Zwicky had inferred from galaxy cluster dynamics in the 1930s, Rubin and Ford confirmed from individual galaxy rotation curves 40 years later. Every galaxy they studied showed the same signature. Every galaxy appeared to be embedded in a dark matter halo. Since then, evidence for dark matter has come from multiple, completely independent observations. Gravitational lensing, the bending of light by mass, reveals concentrations of matter far more massive than the visible galaxies alone can account for. The Bullet Cluster, the result of two galaxy clusters that have recently passed through each other, provides one of the most dramatic illustrations. When the clusters collided, the hot gas between the galaxies was slowed by electromagnetic interactions, ending up between the two clusters. But the dark matter, which doesn't interact electromagnetically, passed straight through and continued outward. Gravitational lensing maps showed two concentrations of mass on either side of the collision, separated from the hot gas. The mass went one way. The gas went another. The pattern is exactly what dark matter predicts. The cosmic microwave background also carries the imprint of dark matter in the early universe. The pattern of tiny temperature fluctuations in the microwave background reflects density fluctuations in the early universe. The relative sizes of those fluctuations, their angular scale, their statistical distribution, are sensitive to the total amount of matter and its type. The Planck satellite's measurements of the microwave background are consistent with a universe containing about 26.8% dark matter, and inconsistent with a universe where there's no dark matter. Dark matter is not an assumption of convenience. It's the conclusion of multiple independent measurements, all pointing to the same answer. It makes up about 27% of the universe's total energy content. It is the dominant form of matter. Normal matter, every atom, in every star, in every galaxy you've ever seen, accounts for only about 5%. And the remaining 68% is dark energy. Together, dark matter and dark energy account for 95% of the universe. The stuff we understand directly, that we can touch and measure and build with, is a 5% minority. We live in a universe mostly made of things we cannot see. Dark energy is in some ways even stranger than dark matter. Dark matter at least has mass. It behaves gravitationally like matter. If you put a lot of it in one place, it attracts more. It clumps. It forms halos. Dark energy does none of this. It's not associated with any particular object or location. It fills all of space uniformly. And unlike matter, which causes gravity that decelerates the expansion of the universe, dark energy has negative pressure, which, in the mathematics of general relativity, accelerates the expansion. It was discovered in 1998, when two independent teams of astronomers were measuring the distances to distant supernovae. Supernovae of a particular type, called Type Ia supernovae, all reach approximately the same peak luminosity. This makes them useful as standard candles. By comparing how bright a Type Ia supernova appears to how bright it actually is, you can calculate how far away it is. The two teams were using this method to measure the rate at which the expansion of the universe was decelerating. They expected to find deceleration. Gravity should be slowing the expansion. What they found instead was that distant supernovae were fainter than expected. Fainter means further. Further means the expansion had been faster than gravity alone could account for. The universe's expansion was not decelerating. It was accelerating. Something was pushing it faster. Something that fills all of space and adds energy to the vacuum. They called it dark energy. The teams were led by Saul Perlmutter and by Brian Schmidt and Adam Rees. They shared the Nobel Prize in Physics in 2011. Dark energy now accounts for 68% of the universe's total energy content. And because it fills all of space uniformly, as space expands, the total amount of dark energy increases. More space means more dark energy. More dark energy accelerates the expansion further. The expansion keeps speeding up. The universe is not coasting. It's accelerating into its future. The accelerating expansion has profound implications, both for the future of the universe and for what we can observe. Every galaxy beyond a certain distance is receding from us faster than light. Not because those galaxies are moving through space faster than light. That would violate special relativity, which sets the speed of light as an absolute speed limit for anything moving through space. But the galaxies aren't moving through space in that sense. They're being carried by the expansion of space itself. Space is stretching, and the galaxies are embedded in it. There's no limit in general relativity on how fast space can expand. The speed of light limits how fast things can move through space. It says nothing about how fast space can move. The most distant galaxies we can currently observe are receding at several times the speed of light. Their light has reached us because it was emitted when those galaxies were much closer. The light has been traveling since before the expansion carried the source to its current extreme distance. New light emitted by those galaxies today will never reach us. The distance is growing faster than the light can close it. As dark energy continues to accelerate the expansion, more and more currently visible galaxies will reach what cosmologists call the cosmic horizon, the boundary beyond which nothing can ever reach us again. As galaxies cross that horizon, their light becomes progressively more redshifted, stretched to longer wavelengths by the expansion of the space it's traveling through. Eventually, the light becomes too stretched, too faint to detect. The galaxy fades from view, not because it was destroyed, because the universe is carrying it away into unreachable distances. In about 150 billion years, if dark energy continues as it currently behaves, only the galaxies of the local group will remain within our cosmic horizon. Everything else will have faded away. The Virgo cluster, the Great Attractor, the Shapley concentration, the thousands of galaxy clusters of the cosmic web, the 2 trillion galaxies of the observable universe. All of it will be gone from view. Future astronomers, if there are any, will look out at the sky and see almost nothing. Just the merged local group, Milky Way, and its satellite galaxies, in an otherwise dark sky. They will have no way to know the rest of the universe exists. The cosmic microwave background will have been redshifted to such long wavelengths that it will be undetectable. The evidence for the Big Bang will be gone. Evidence of the cosmic web will be gone. Evidence of the large-scale structure, the filaments, the voids, the superclusters, all gone. If those future astronomers develop cosmology, they'll likely conclude the universe is small. Just the local group. Maybe a few billion light-years across, they might estimate, based on the distances to their nearest neighbors. They'll be profoundly wrong. They'll have no way to know it. We are fortunate, in a cosmic sense, to exist now. The universe has been expanding long enough to form galaxies, stars, planets, and life. But not so long that all the evidence of its large-scale structure has been erased. We can still see the cosmic web. We can still detect the microwave background. We can still observe the 2 trillion galaxies. A billion years ago, the tools didn't exist to understand what we see. 100 billion years from now, most of what we see will be gone. We exist at the brief window when it's all there, and we've developed the means to read it. The history of humanity's understanding of cosmic scale has always moved in the same direction. Bigger. Every time we've built better instruments, we've discovered more. Every time we've revised our estimates, the universe has turned out to be larger than the previous estimates suggested. For most of human history, the stars appeared to be points of light affixed to a sphere surrounding Earth. The ancient Greeks argued about the distances to the stars and whether the Earth moved. Most concluded it didn't. The distances involved in a moving Earth seemed too vast to reconcile with the lack of observed parallax. They were right about the parallax. They were wrong about the conclusion. The distances were just so large that the parallax was undetectable with the naked eye. Copernicus placed the Sun, not Earth, at the center of the solar system in the 16th century. That was significant. But it didn't change the implied size of the universe dramatically. The stars could still be relatively close. Giordano Bruno, in the late 16th century, proposed that the stars were other suns, possibly surrounded by other planets and other forms of life. He was burned for a combination of heretical views, and his cosmological ideas were not the primary charge. but his intuition about the stars turned out to be correct. The first reliable estimates of stellar distances came in the 19th century, when astronomers successfully measured the parallax of nearby stars. The parallax of a star is the tiny shift in its apparent position as Earth moves from one side of its orbit to the other. By measuring that shift, you can calculate the distance. The nearest star, Proxima Centauri, has a parallax of about 0.77 arcseconds. An arcsecond is 1/3000/600th of a degree. Even the nearest star is so far away that its positional shift is barely detectable. The measurement of stellar parallaxes revealed a universe much larger than most people had imagined. Nearby stars were light years away, not months away. And the distant stars were even further. But the Milky Way, the full extent of our galaxy, wasn't mapped until the early 20th century. And even then, its size was disputed. The great debate of 1920 between Harlow Shapley and Heber Curtis was ostensibly about the size of the Milky Way and the nature of the spiral nebulae. Shapley thought the Milky Way was enormous, perhaps 300,000 light-years across, and that the spiral nebulae were objects within it. Curtis thought the Milky Way was smaller, and that the spiral nebulae were separate island universes, galaxies in their own right. Both men had good evidence for their positions, and both were partially right. The Milky Way is large, though not quite as large as Shapley thought, and the spiral nebulae are separate galaxies, as Curtis believed. The resolution came in the 1920s through Edwin Hubble's measurement of Cepheid variable stars in the Andromeda Nebula. Cepheid variables are stars that pulsate in brightness at a rate directly related to their true luminosity. Henrietta Swan Leavitt had established this relationship by systematically studying Cepheids in the Small Magellanic Cloud. By comparing the pulsation period to the apparent brightness, you can calculate the distance. Hubble applied this method to Cepheids he identified in the Andromeda Nebula using the Hooker telescope on Mount Wilson. His distance estimate was about 900,000 light-years, far too distant for Andromeda to be inside the Milky Way. Andromeda was a separate galaxy. The universe was not the Milky Way. The Milky Way was one galaxy among many. Hubble's paper in 1925 confirmed Curtis's position and fundamentally expanded the known universe. Then came the redshift measurements. Hubble systematically measured the velocities of dozens of galaxies and found that almost all of them were receding. The further away they were, the faster they were moving. In 1929, he published the relationship that now bears his name. Velocity is proportional to distance. Double the distance, double the recession speed. This is the observational signature of an expanding universe. Not galaxies flying through space outward from a central explosion. Space itself, stretching, carrying all galaxies apart from all others. Every point in the universe moving away from every other point. Not because anything is moving through space, but because space itself is growing. Hubble's law implied a beginning. If you run the expansion backward, everything was once closer together. At some point in the past, everything was in the same place. That point, the beginning of space and time as we understand them, is the Big Bang. The Big Bang is one of the most widely understood and most widely misunderstood concepts in science. The common image is of an explosion, a point in space erupting outward into a pre-existing void. That image is wrong in several important ways. There was no pre-existing void. There was no point in space where it happened. Space itself began at the Big Bang. Time itself began at the Big Bang. Before the Big Bang, in the classical picture, there is no before. The question of what existed before the Big Bang is similar to asking what's north of the North Pole. The language of before assumes time existed. At the Big Bang, time was created along with space. The Big Bang happened everywhere, simultaneously, because everywhere was the same place. In the first tiny fraction of a second, the universe was unimaginably hot and dense. A state of matter and energy that has no comparison in ordinary experience. Temperatures of trillions upon trillions of degrees. Densities so extreme that the physics governing ordinary matter breaks down. Quarks and gluons, the constituents of protons and neutrons, were not yet confined into those particles. They moved freely in a primordial plasma. As the universe expanded and cooled, quarks and gluons became confined into protons and neutrons. The temperature dropped below the threshold needed to keep them free. A few minutes after the Big Bang, nuclear reactions assembled protons and neutrons into the first atomic nuclei. Helium, a small amount of deuterium, a trace of lithium. This process, Big Bang nucleosynthesis, produced the composition of light elements we observe in the oldest stars. About 75% hydrogen, about 25% helium by mass, with trace amounts of heavier elements. This ratio is one of the observational pillars of Big Bang cosmology. It matches the predictions of the model to extraordinary precision. For 380,000 years after the Big Bang, the universe remained opaque. It was too hot for electrons to remain bound to atomic nuclei. Free electrons scattered light in all directions, making the universe foggy, like the interior of a cloud. Photons couldn't travel more than a short distance before scattering off another electron. Then, when the temperature dropped to about 3,000 degrees, electrons and protons could finally combine into neutral hydrogen atoms. The electrons were captured. The fog cleared. For the first time, light could travel freely through the universe. The photons that had been trapped in the plasma were suddenly free. They streamed outward in all directions. Those photons are still traveling today, stretched by the expansion of the universe from their original visible light wavelengths all the way down to microwave wavelengths. That's the cosmic microwave background, the oldest light we can detect. A faint glow coming from all directions equally, a three-dimensional snapshot of the universe at 380,000 years old. When COBE, the cosmic background explorer, mapped the microwave background in the early 1990s, it found something crucial. The background wasn't perfectly uniform. It had tiny temperature fluctuations, regions fractionally hotter and fractionally cooler than the average. The hot spots were regions slightly denser than average. The cool spots were regions slightly less dense. Those fluctuations are the seeds of all the structure in the universe today. Every galaxy, every cluster, every filament of the cosmic web grew from the amplification of those tiny temperature differences. The WMAP satellite refined the map in the early 2000s. The Planck satellite, launched in 2009, produced the most detailed map of the microwave background ever made. Temperature variations measured to millionths of a degree across the full sky. From Planck's data, cosmologists have determined the age of the universe with sub-1% precision, 13.8 billion years. The composition, 4.9% normal matter, 26.8% dark matter, 68.3% dark energy. The geometry of space, flat to within less than 0.5%, and the statistical properties of the original density fluctuations which constrain the physics of inflation and the very earliest moments of cosmic history. All of that from studying the oldest light in the universe, a light that left its source before there were any stars, before there were any galaxies, before there was any structure at all, when the universe was a smooth, expanding, cooling plasma. And that light is arriving at Earth right now, from every direction, carrying its ancient information. The microwave background is the universe's own earliest record, and we can read it. After the microwave background was released, the universe entered what cosmologists call the cosmic dark ages. There were no stars yet, no galaxies, no light sources, just expanding, cooling gas, mostly hydrogen and helium, slightly unevenly distributed, with small overdense regions slowly gathering matter by gravity. For about 100 million years, the universe was dark. Then, the first stars ignited. The first stars that formed, called population. 3 stars in the astronomical classification system were likely very different from any stars alive today. They formed from gas that contained almost no heavy elements. No carbon, no oxygen, no iron. Just hydrogen and helium from the Big Bang. Models suggest these first stars may have been extremely massive, possibly hundreds of times the mass of our Sun. They burned extraordinarily hot and bright. They lived for only a few million years before their cores collapsed, and they exploded as supernovae. Those explosions were catastrophic, but they were also generative. They scattered the first heavy elements, forged in the cores of those massive stars, into the surrounding gas, carbon, oxygen, nitrogen, silicon, elements that had never existed in the universe before. The second generation of stars formed from gas, now enriched with those heavy elements. They were somewhat different from the first, and they, in turn, forged more elements and scattered them in their deaths. Our Sun is a third-generation star. The heavy elements in its composition, the iron that makes up Earth's core, the carbon that forms the backbone of every biological molecule, the oxygen in the atmosphere, were made in 2 previous generations of stars, scattered into space by their supernovae, incorporated into the molecular cloud that collapsed to form the solar system 4.5 billion years ago. We are, in a very literal chemical sense, made of stars. The universe had to go through 2 generations of stellar life and death before it could make the ingredients for us. The first galaxies began to form within the first billion years. Small, irregular collections of millions to billions of stars, colliding and merging with each other, growing larger over time. The Milky Way wasn't always the 100,000 light-year disk it is today. It assembled over billions of years, through mergers with hundreds of smaller galaxies. It's still absorbing smaller galaxies now, and it will merge with Andromeda in the future. Galaxies grow by eating smaller galaxies. The largest galaxies today are the result of billions of years of accumulation. The physics underlying everything we've discussed has a remarkable unity to it. The same equations that govern the orbit of Earth around the Sun, derived by Isaac Newton in the 17th century and refined by Einstein in the early 20th, are the equations that govern the orbit of the Sun around the Milky Way. The orbit of the Milky Way around Laniakea's center of mass, and the large-scale motion of everything in the cosmic web. Gravity is scale invariant. The inverse square law that makes apples fall from trees is the same inverse square law that shaped the cosmic web. Newton described gravity as a force between masses, Einstein reframed it as geometry. Masses curve, space-time, and other masses follow the curves. The curvature of space-time by the mass of Earth is what keeps you on the ground. The curvature of space-time by the mass of the Sun is what keeps the planets in orbit. The curvature of space-time by the mass of the Milky Way is what keeps the stars orbiting the galactic center. And the curvature of space-time by the mass of galaxy clusters is what shapes the motion of galaxies through the cosmic web. One set of equations. One description of reality. Applied at every scale, from the size of a planet's orbit to the size of the observable universe. Einstein's general theory of relativity also predicts that space-time can propagate ripples. Not waves in a medium, the way sound waves propagate through air. Waves in the fabric of space-time itself. When massive objects accelerate, they disturb the curvature of space-time around them. Those disturbances propagate outward at the speed of light as gravitational waves. Einstein predicted this in 1915. For 100 years, it remained purely theoretical. The waves were too small to measure with any existing technology. Then, in September of 2015, the LIGO detectors, the Laser Interferometer Gravitational Wave Observatory, detected a signal. 2 detectors, one in Louisiana and one in Washington state, each with laser beams traveling down arms about 2.5 miles long, saw the same pattern at almost the same instant. A tiny oscillation in the length of the arms. The signal lasted a fraction of a second. It was the gravitational wave signature of 2 black holes, each about 30 times the mass of the Sun, spiraling together and merging over 1 billion years ago. The merger happened 1 billion light-years away. The gravitational waves from that event have been traveling through space ever since. When they reached Earth, the LIGO detectors responded. The amount by which the arms changed length during the detection was about 1,000th the diameter of a proton. The precision required to measure that is extraordinary. LIGO is perhaps the most sensitive measurement device ever built. The teams that led the detection, led by Kip Thorne, Rainer Weiss, and Barry Barish, received the Nobel Prize in Physics in 2017. Since the first detection, dozens more gravitational wave events have been observed, merging black holes of various masses, merging neutron stars. In 2017, a neutron star merger was detected in both gravitational waves and in light. Telescopes around the world were alerted and pointed at the location. The observations confirmed that neutron star mergers produce heavy elements, including gold and platinum. Every gold atom on Earth was created in a neutron star merger billions of years ago and scattered into space. It was incorporated into the gas cloud that formed the solar system. It's been sitting in your jewelry or in the gold contacts of your electronics ever since. Gravitational wave astronomy has opened a new window on the universe. Light has been the primary messenger in astronomy for almost all of human history. Now we can detect the universe through the ripples in space-time itself. And the sources of those ripples exist throughout the observable universe. Black holes are merging in distant galaxies right now. Those mergers are sending gravitational waves through space. Some of those waves will reach Earth thousands or millions of years from now. The universe is speaking to us in multiple languages. We're only just beginning to learn them. There's a phenomenon in the observable universe called gravitational lensing that provides some of the most dramatic evidence for the scale of what's out there. When light from a distant galaxy passes near a massive object, the gravity of that object bends the path of the light. The same way a lens bends light, but through the curvature of space-time rather than through the refraction of glass. This is called gravitational lensing. At small scales, a single star in the foreground can bend the light from a more distant star, temporarily brightening it. This is called microlensing, and it's used to detect planets around distant stars and to probe the distribution of dark matter. At larger scales, a galaxy or cluster of galaxies can bend and distort the light from much more distant objects. The images of background galaxies get stretched into arcs, sometimes into near-complete rings, when the alignment between the source, the lens, and the observer is particularly good. These Einstein rings, as they're called, were predicted by Einstein's general relativity and confirmed observationally. The Hubble Space Telescope has captured spectacular examples of gravitational lensing, showing background galaxies distorted into sweeping arcs by foreground clusters. These images are not just beautiful, they're scientifically valuable. By measuring how much the background galaxy's image is distorted, you can infer the mass of the foreground lens. And consistently, the mass inferred from gravitational lensing is much larger than the mass of the visible galaxies and gas in the foreground cluster. The difference is dark matter. Gravitational lensing maps the total mass of a cluster, visible and dark together. And those maps show dark matter halos surrounding the visible galaxies, extending far beyond where the stars are. Galaxy clusters, like the Bullet cluster, where two clusters have recently collided, show the dark matter and the ordinary gas separated by the collision. The gas, which interacts electromagnetically, was slowed by the interaction and ended up between the two clusters. The dark matter, which doesn't interact electromagnetically, passed straight through and continued outward with the galaxies. Lensing maps show the dark matter on either side of the collision, offset from the gas. The pattern is exactly what dark matter predicts. It's one of the most visually compelling pieces of evidence for dark matter ever obtained. Gravitational lensing is also used to probe the distribution of dark matter on the largest scales. As light from distant galaxies travels toward us through the cosmic web, it gets slightly distorted by the large-scale distribution of mass. Not dramatically, not into rings, but in statistically detectable ways. By measuring the shapes of millions of background galaxies and looking for subtle correlations in those shapes, astronomers can map the distribution of mass in the universe on scales of hundreds of millions of light-years. This technique, called weak gravitational lensing or cosmic shear, is one of the most powerful tools for studying the large-scale structure of the universe. Current surveys like the Dark Energy Survey have mapped the distribution of mass across large portions of the sky. Future surveys, like the Vera Rubin Observatory's Legacy Survey of Space and Time, will extend this mapping to unprecedented scale. The goal is to constrain the nature of dark energy and dark matter more precisely. To understand not just that they exist, but what they actually are. And that's where cosmology currently stands. We know the universe contains dark matter and dark energy. We know their abundances. We know their effects. We understand them well enough to make accurate predictions about the large-scale structure of the universe. But we don't know what they are at a fundamental level. We don't know what particle dark matter is. We don't know what mechanism generates dark energy. These are the deepest open questions in physics, and their answers, when they come, may change our understanding of the universe as dramatically as any previous discovery. There is one more aspect of this comparison worth dwelling on. The observable universe, for all its 93 billion light-year diameter, is not a perfect sphere of uniform content. It looks different in different directions, in subtle ways. At the very largest scales, the universe appears to be homogeneous and isotropic, meaning it looks the same everywhere and in every direction when averaged over regions large enough. But there are large-scale features, the dipole anisotropy in the cosmic microwave background, a slightly higher temperature in one direction and a slightly lower temperature in the opposite direction. This is caused by our own motion through space. The Milky Way is moving through the cosmic microwave background at a certain velocity, and that motion, Doppler, shifts the temperature of the background. By measuring the dipole, astronomers can determine our motion relative to the microwave background. We're moving at about 230 miles per second in the direction of the constellation Leo. That's our total motion relative to the background. It includes the Sun's motion around the Milky Way, the Milky Way's motion within the local group, and the local group's peculiar motion within the large-scale cosmic flow. This velocity is the result of all the gravitational influences on our position, from the Virgo cluster to the Great Attractor to the Shapley concentration. We're not stationary. We're embedded in a gravitational web that's been sculpting our trajectory through space for billions of years. And the cosmic microwave background, arriving from all directions, gives us a fixed reference frame against which to measure that motion. It's the closest thing the universe has to an absolute background. Everything else is moving relative to something. The microwave background is the frame set by the expansion of the universe itself. We're moving through it at about 230 miles per second. Not fast by cosmic standards, but not standing still. Nothing in the universe stands still. There's something particular about the relationship between time and observation that deserves its own moment. When astronomers say they're observing the early universe, they're not speaking metaphorically. They're literally looking back in time. The universe, at very large distances, is not visible to us as it is now. It's visible to us as it was when the light we're seeing was emitted. And in a universe that's been evolving for 13.8 billion years, that's a substantial difference. The Andromeda Galaxy looks, in our telescopes, as it was 2.5 million years ago. The Virgo cluster looks as it was 50 million years ago. Distant quasars appear as they were billions of years ago, when supermassive black holes were actively feeding and the universe was younger and denser. The galaxies at the edge of the observable universe appear as they were over 13 billion years ago, in the first billion years of cosmic history. We are surrounded by time as much as by space. Every distance corresponds to a moment in the past. The observable universe is a kind of four-dimensional structure where looking outward and looking backward in time are the same action. This means that when we observe the large-scale structure of the universe, we're not seeing a static snapshot. We're seeing the universe at different ages simultaneously. In the nearby universe, we see galaxies as they are now. In the middle distance, we see them as they were hundreds of millions or billions of years ago. In the far distance, we see the universe before most galaxies had formed. And at the very edge of what we can detect, we see the universe before stars existed at all. This layered view through time has been one of the most powerful tools in cosmology. It lets us watch the universe evolve. We don't have to model it from scratch and hope the model is right. We can observe different epochs directly and compare them. We can see that galaxies were smaller in the past, more irregular, more actively forming stars. We can see that the cosmic star formation rate peaked about 10 billion years ago and has been declining since. We can see that the clustering of galaxies has increased as the universe has aged and the cosmic web has become more organized. We can trace the evolution of galaxy morphology from the irregular clumps of the early universe to the spirals and ellipticals of today. The Hubble Space Telescope's deep fields gave us the first comprehensive look across cosmic time. The James Webb Space Telescope has extended that look to earlier epochs, and what we see is a universe that has been changing continuously, organizing itself into larger and more complex structures over billions of years. From near uniformity just after the Big Bang, through the first stars and galaxies, through the peak of star formation to the relatively quiet present, the Milky Way is part of this story. It began forming early, perhaps as early as 12 or 13 billion years ago. It's been growing since, through mergers with smaller galaxies and the ongoing accretion of gas from its surroundings. The stars in its halo, some of the oldest in the galaxy, date to its earliest phase. The Sun and Earth formed 4.5 billion years ago, when the galaxy was already mature. We're newcomers, relatively speaking. The galaxy had billions of years of history before our solar system existed, and it will continue for billions of years after the Sun burns out. The Milky Way will outlast us by an enormous margin. After the merger with Andromeda, Milkomeda will continue for trillions of years. Long after the last new stars have formed, its population of stellar remnants, white dwarfs, neutron stars, and black holes will persist. Eventually, even those will fade or be disrupted. But that's unimaginably far in the future. For now, the galaxy is alive. Stars are forming. Supernovae are exploding. Planets are circling stars. And on one of those planets, here, a species that's been around for a few 100,000 years has spent the last 4 centuries measuring the universe it lives in and discovering that it's almost incomprehensibly vast. There are questions about the universe that physics can approach but not fully resolve. The most fundamental is whether the observable universe is the whole universe or just a small part of it. The observable universe, with its radius of 46 billion light-years, is defined by what we can see, by the limit imposed by the finite speed of light and the finite age of the universe. But there's no reason the universe has to stop at that boundary. The observable universe is not a wall. It's a horizon. Just as the horizon you see when you stand on a beach doesn't mark the edge of the ocean, the cosmic horizon doesn't mark the edge of space. Beyond the horizon, there's almost certainly more. We just can't see it. The question is, how much more? Current measurements of the geometry of space suggest the universe is flat. The Planck satellite measured the curvature of space to be 0 to within about 0.5%. If the universe is flat, and if it's infinite, then the structures we observe in the observable universe, the cosmic web, the galaxy clusters, the filaments, continue indefinitely beyond our horizon. They don't repeat identically. But, on large enough scales, in an infinite flat universe, every configuration of matter that has any probability of existing will occur. Because an infinite universe contains infinite opportunities for probability to play out. This is a genuinely strange implication, and physicists differ on how seriously to take it. Some treat it as a meaningful physical reality. An infinite universe implies infinite copies of every possible arrangement of matter. Others treat it as a sign that our models have reached the edge of what's physically meaningful. The alternative geometries also have their own implications. If the universe has a positive curvature, like the surface of a four-dimensional sphere. It's finite but unbounded. Travel far enough in a straight line and you return to where you started, like traveling around the surface of the Earth. But current measurements don't support this. The universe is flat, or very close to it. Even within the flat geometry, the actual extent of the universe could be any size. A flat universe could be exactly the size of the observable universe, or it could be 10 times larger, or 1,000,000 times larger, or infinite. The flatness measurement doesn't distinguish between these. A perfectly smooth, flat surface, stretching a millimeter, is just as flat as one stretching a light year. Flatness doesn't imply size. We know the observable universe contains at least 2 trillion galaxies and spans 93 billion light-years. The actual universe almost certainly extends beyond that. By how much, we cannot say. The observable universe may be a tiny fraction of the whole, or it may be essentially the whole thing. Current physics cannot tell us which. What we have is the observable universe. And that observable universe is already so large that our galaxy, for all its 100 billion stars, is a microscopic feature within it. The actual universe could dwarf even that by any factor you care to imagine. Let's walk through the scale ladder one more time, slowly. Not to repeat the numbers, but to feel the weight of each transition. The Milky Way disk, 100,000 light-years across. When light leaves one edge of the visible Milky Way heading for the other, civilizations rise and fall before it arrives. Languages spoken when that light departed are extinct. Technologies used when that light departed are forgotten, and the light is still on its way. The local group, about 10 million light-years across. Andromeda's light, arriving in your eye right now, left its source 2.5 million years ago. The entire span of the local group is so great that light crossing it takes millions of years. The Virgo supercluster, about 110 million light-years. Light crossing the Virgo supercluster takes longer than the age of complex animal life on Earth. Laniakea, 500 million light-years. Its diameter in light-years is older than the earliest animals with hard shells, older than the Cambrian explosion. The Sloan Great Wall, 1.37 billion light-years. Longer than the interval since the first eukaryotic cells appeared. The observable universe, 93 billion light-years. 7 times the age of the universe itself, in terms of light travel time. At each step, the previous structure becomes infinitesimally small. The Milky Way, enormous by human standards, is to Laniakea what a grain of sand is to a mountain range. And Laniakea is to the observable universe what a grain of sand is to a planet. The numbers are not metaphorical. They're measured. They're the result of decades of observations with increasingly sophisticated instruments. Radio telescopes, optical telescopes, X-ray satellites, infrared observatories, gravitational wave detectors, all of them converging on the same picture. A universe of almost incomprehensible scale, organized into a structure as complex as it is vast. And at one small location within that structure, a particular galaxy called the Milky Way, orbiting at a particular distance from a particular galaxy center, a particular star with a particular planet circling it. There's a species that managed to figure most of this out. That might be the strangest part of all of this. Not that the universe is vast, but that the stuff inside it assembled from hydrogen and helium forged in the Big Bang and heavier elements forged in stars, eventually became curious enough to measure itself. There's another dimension to the comparison between the Milky Way and the universe that doesn't get discussed often enough. It's not just a spatial comparison. It's a temporal one. The universe, at different distances from us, is observed at different points in its history. When you look at the Andromeda galaxy, you're seeing it as it was 2.5 million years ago. When you look at the Virgo cluster, you're seeing it as it was 50 million years ago. When you observe galaxies at the edge of the observable universe, you're seeing them as they were over 13 billion years ago. The light took that long to get here. You're not looking across space. You're looking backward through time. The observable universe is not a snapshot of how the universe looks right now. It's a layered historical record. Every shell of distance represents a different era of cosmic history. The nearby universe shows galaxies as they currently are. The middle distance shows them as they were hundreds of millions or billions of years ago. The far distance shows the early universe, before the cosmic web had fully formed, before most stars had been born. And at the furthest observable distance, the surface of last scattering, we see the universe before stars existed at all. Just the cooling plasma of the early cosmos, preserved in the microwave background. This has a profound implication for how we study the universe. We can observe cosmic history directly. We don't have to model it from first principles and hope our models are right. We can look at different distances and see different epochs. We can compare the universe at 1 billion years old to the universe at 5 billion years, to the universe at 10 billion years, to the universe now. We can trace how galaxies formed, how they grew, how they changed over time. And what this record shows is that the universe we live in now is not the universe as it always was. In the early universe, galaxies were smaller, more irregular, more active. Star formation rates were much higher. The average galaxy was making new stars far more vigorously than the average galaxy does today. Galaxy mergers were more frequent. The universe was smaller and denser, so galaxies were closer together and interactions were more common. Supermassive black holes at galactic centers were more active, feeding more intensely on surrounding gas and producing the brilliant quasars that are visible across enormous distances. Quasars were the most luminous objects in the universe in its early history. They outshone their entire host galaxies by factors of hundreds. They're powered by supermassive black holes, consuming gas at prodigious rates, converting mass to energy through the same physics that makes a black hole's accretion disk one of the most efficient energy conversion processes in nature. Today, quasars are rare. Most supermassive black holes in the present universe are quiescent. Their fuel supply has been exhausted. The Milky Way's central black hole, Sagittarius A, is almost completely inactive today. It's surrounded by a sparse supply of gas and occasionally swallows a small amount, flaring briefly in X-rays. But it's nothing like the active black holes of the early universe. It's in a quiet phase. The universe has grown quieter over its history. The intensity of star formation has declined. The frequency of galaxy mergers has declined. The activity of supermassive black holes has declined. We live in the middle age of the universe, not the frenzied youth of the first few billion years. Not the cold, dark, far future when stars have burned out. The long, calm, middle period when the structures formed in the early universe are stable and settled. Galaxies like the Milky Way are in a relatively quiet phase of their lives, forming new stars at modest rates, orbiting their galactic centers, embedded in large-scale structures that change only over billions of years. This is, in cosmological terms, a peaceful era. Now bring all of this together and think about what the comparison really means. The Milky Way is 100,000 light-years across. It contains somewhere between 100 billion and 400 billion stars. It has a supermassive black hole at its center. It has spiral arms, star-forming regions, globular clusters, a stellar halo, and a dark matter halo 6 times its visible size. It has a rich internal structure. It has a complex history. It is, by any human standard, incomprehensibly large and complex. And the observable universe contains about 2 trillion of them, in a volume 93 billion light-years across, organized into a web of filaments and voids that extends to the edge of what we can see, and almost certainly beyond, containing 5% of its energy in the form of ordinary matter, 27% in the form of dark matter, 68% in the form of dark energy, all of it governed by the same physical laws that govern the Milky Way. The same laws that hold you to the Earth and keep the Earth in orbit around the Sun and keep the Sun orbiting the Milky Way. The same laws, applied to the entire observable universe, working the same way from one end to the other, from the smallest detail to the largest structure. There's something almost impossible to accept about this, even once you understand it intellectually. The Milky Way, which contains hundreds of billions of stars, which would take light 100,000 years to cross, which has been forming stars for over 10 billion years. That object is a microscopic feature of the observable universe, one of 2 trillion similar objects, spread across a volume that's 930,000 times its own diameter. And that observable universe is not the whole universe. It's just the part whose light has had time to reach us. We don't know how much further the actual universe extends. It could be 10 times the observable. It could be 1 trillion times. It could be infinite. The question is genuinely open. What we know is the observable part, and the observable part alone is already more than our minds were built to hold. The process of coming to understand all of this didn't happen quickly. It has taken about 400 years of increasingly precise astronomy, from Galileo pointing his telescope at the sky in the early 17th century to the James Webb Space Telescope delivering images of the first billion years of the universe. Each generation of instruments revealed more. Each generation of observations expanded the known universe. Galileo's telescope showed that the Milky Way was made of individual stars, too numerous to count with the naked eye. 18th century astronomers began to map the positions and distances of those stars. William Herschel constructed a rough model of the Milky Way's shape in the late 18th century, though it placed the Sun near the center, which was wrong. By the early 20th century, the debate about the size of the Milky Way and the nature of the spiral nebulae was unresolved. Hubble resolved it. Then, Hubble measured the expansion. Then, cosmologists deduced the Big Bang. Then, radio telescopes discovered the microwave background. Then, satellites mapped it with extraordinary precision. Then, ground-based surveys mapped the large-scale structure of galaxies. Then the Hubble Space Telescope showed galaxies in every patch of apparently empty sky. Then, the census of galaxies was revised upward to 2 trillion. Then Webb began observing the first billion years of cosmic history. At every step, the universe turned out to be more than the previous step suggested. More galaxies, more structure, more history. A larger stage. There's no reason to think we've reached the last step. Future instruments will see further, with higher resolution, in more wavelengths. They'll reveal features of the cosmic web we haven't yet resolved. They'll push the frontier of observable history closer to the Big Bang. They'll better constrain the nature of dark matter and dark energy. They'll tell us more about the early universe and the first galaxies. And each step will likely make the universe larger, more complex, more structured than the step before it suggested. The universe has, so far, always been bigger than our previous best estimate. It's a reasonable prior that it will continue to be. There's a concept in physics that's worth naming in this context. It's called the Copernican principle, or sometimes the mediocrity principle. The idea is that we should not assume our position in the universe is special. Copernicus removed Earth from the center of the solar system. Subsequent discoveries removed the Sun from the center of the Milky Way. And Hubble's discovery that the universe is expanding removed any possibility of a center to the observable universe at all. In an expanding universe, every point in space sees every other point receding from it. There's no center. Every point is equivalent. The Copernican principle says that if there's no reason to think we're at a special position, we should assume we're not. We should assume we're typical. The Milky Way is a typical galaxy, roughly in the middle of the galaxy mass function. Not the most massive, not the least. Our Sun is a typical star. Not the most massive, not the least. Not in the most crowded region of the galaxy, not in the least crowded. And our era, the current age of the universe, is not a special moment in cosmic history. Or at least, that's one view. Another view notes that intelligent life seems to require particular conditions. Stars that burn steadily for billions of years. Heavy elements for rocky planets and complex chemistry. An environment stable enough for evolution to run its course. These conditions weren't present in the very early universe. They require time. They require stars to have lived and died. They require chemistry to develop. In that sense, the timing of our existence may not be arbitrary. We exist in the era when conditions for life have been met for long enough that life could actually develop. Earlier would have meant no heavy elements. Much later would mean stars burning out, galaxies fading. We're in the window. Whether this makes our moment special in a meaningful sense, or whether the window is so long that our existence within it is simply unremarkable, is a question that's genuinely open. What's not open is the scale. We exist in a galaxy that is 930,000 times smaller than the observable universe. The observable universe contains 2 trillion galaxies. The actual universe is almost certainly larger still. Whatever significance or insignificance we assign to our position within it, the scale is what it is. And the scale is extraordinary. Let's take a moment to think about what it means, practically, to be a galaxy inside the observable universe. Not philosophically, physically. The Milky Way is, in the cosmic web, a small object in a medium-density environment. It sits in the local group, which sits in the outskirts of Laniakea, which sits in one part of the cosmic web among many. The nearest large concentrations of galaxies, the Virgo cluster, are tens of millions of light-years away. The galaxy is too far from any cluster to be significantly affected by cluster environments. It's not being ram pressure stripped. It's not being tidally disrupted by a passing massive galaxy. It's in a relatively isolated position. It has satellite galaxies, the Magellanic Clouds, and dozens of smaller dwarfs, which it's gradually absorbing. It has a neighbor, Andromeda, with which it will eventually merge. But on the cosmic scale of the web, our position is peripheral, in the outskirts of a supercluster, in a group of medium density, far from any of the most dramatic cosmic environments. This may have consequences for life. Dense cluster environments are hostile. The radiation from nearby active galaxies and frequent supernovae can sterilize planetary surfaces. Tidal interactions between galaxies can disrupt planetary orbits. The high density of objects increases the probability of encounters that destabilize solar systems. Our relatively quiet corner of the cosmic web is, in that sense, a more hospitable place for complex life to develop over billions of years. Whether other corners of the web, other positions within the 2 trillion galaxies of the observable universe host life of comparable or greater complexity, we don't know. We have no evidence either way. The one data point we have is our own existence. And our existence is associated with a particular kind of position. In the disk of a mid-sized spiral galaxy, in a medium-density region of a supercluster, in the middle age of the universe. What this tells us about the prevalence of life elsewhere is, so far, unresolved. The Fermi paradox. The question of why we don't observe evidence of other technologically advanced civilizations in a universe with 2 trillion galaxies and potentially trillions of planets remains one of the most genuinely puzzling, open problems in science. With numbers this large, even a very low probability of complex life per galaxy should produce, statistically, an enormous number of complex civilizations in the observable universe. And yet, we see no evidence of any beyond our own. The explanations range from the mundane, we haven't looked hard enough, or the signals are too weak, to the profound, complex life is genuinely rare, or civilizations don't survive long enough to be detectable. The answer is not known. The scale of the universe doesn't resolve the paradox. It makes it sharper. The comparison between the Milky Way and the observable universe is not just a numbers exercise. It's a reorientation. It's what happens when you take the thing that seems largest in your frame of reference, the galaxy that fills the night sky, that contains more stars than you could count in thousands of lifetimes, and you put it next to the actual context it exists in. And the context is 930,000 times larger. The Milky Way is not a small object. It's enormous. But the universe contains 2 trillion of them, and the universe may itself be a small corner of something larger still. At every scale we've explored, the pattern has been the same. There's more. More structure, more extent, more history, more complexity. The universe has never turned out to be the size we thought it was. It's always turned out to be bigger, and we've always turned out to be smaller within it. Not smaller in importance, necessarily. That's a philosophical question, but smaller in position, more peripheral. One part of an ever-expanding context. Standing outside on a clear night, looking up at the Milky Way, you're looking at something that is simultaneously vast and microscopic. Vast by any human measure. Microscopic by the measure of the observable universe. Both are true. And holding both of those truths simultaneously is what it feels like to actually understand where you are in the cosmos. You're inside one galaxy, one of 2 trillion, in a universe 93 billion light-years across, that may itself be a small fraction of the whole. And you're standing on a rocky planet, orbiting a star 26,000 light-years from its galaxy's center, in a quiet corner of a supercluster that's been gravitationally assembling itself for billions of years. And you know all of this, because some of the matter in this universe, assembled in this galaxy, on this planet, over the last few billion years, developed the capacity to measure the universe and understand the answer. That remains, for all the numbers, one of the more striking things about the observable universe. It produced something that could observe it. When you look up at the night sky and find the Milky Way, that faint band of light crossing the sky from horizon to horizon, understand what you're seeing. You're looking from inside a disk of hundreds of billions of stars. Light from those stars has been traveling toward you for years, centuries, tens of thousands of years, depending on the star. That band of light represents a structure that would take 100,000 years to cross at the speed of light. And that structure is surrounded by a dark matter halo, 6 times its visible diameter. And it sits in the local group, 100 times its diameter. And the local group sits in the Virgo supercluster, 1,000 times the galaxy's diameter. And the Virgo supercluster is one small part of Laniakea, 5,000 times the galaxy's diameter. And Laniakea sits in the cosmic web, which fills the observable universe, 930,000 times the galaxy's diameter. And 2 trillion galaxies are scattered through that web, each one comparable in scale to the Milky Way. And beyond the edge of what we can observe, the universe almost certainly continues. By how much, we don't know. That's what you're standing inside of. That's where you are. Good night.